welcome. In this video, I'm going to be working AP Pre-Cal Homework 8.2. So we're going to be solving some slightly more advanced trig equations, ones that require Pythagorean identities, and doing a little bit of show that type problems that show that one function is equivalent to another. Two representations are equivalent. And I don't know why the quality of my PDF is so bad, but I'm just going to go with it. I think it's going to be all right. All right, so find the intersections. We're just going to set the two things equal to each other and solve. Did it give me, yeah, on the interval 0 to 2 pi, so that's going to limit our level of responsibility here. So we're going to set the two things equal to each other, so 2 cosine squared x equals cosine x. And rather than dividing both sides of this equation by cosine x, which could lose us solutions, the places where cosine equals 0, we wouldn't be able to see those, because you can't really see when you divide both sides of an equation by 0, because it's not really keeping the truth of the equation. But that's a whole different discussion. Hopefully I went into that with you in the lesson. We're going to set this thing equal to 0. Okay, and maybe just this once, I'll write it as cosine of x squared, but I think, kind of leaving that in the last lesson. And then now I'm going to want to factor out 1 power of cosine x. So cosine x multiplied by, 2 times 1 power of cosine x, and then minus 1. Okay, and if it makes you feel better, I can put parentheses around that one. That would probably be for the best. So either cosine x equals 0, or maybe 2 cosine x minus 1 equals 0. Okay, so that would be when 2 cosine x equaled 1, which would be when cosine x equaled 1/2. All right, so I think I'm just going to go to a circle over here. Just work in this area. All right, figuring where cosine equals 0. Okay, that's where the x-coordinate on the unit circle is 0, or where the horizontal displacement from the y-axis is 0. That's going to be here. I'm going to have x equals pi over 2 and x equals 3 pi over 2. Then I'm going to also have the places where cosine x equals 1/2. And 1/2, that's not very far over on the unit circle, so that would be, like equivalent to the short leg of a 30, 60, 90 triangle. So I'd have a 60-degree reference angle. That would be up here, and down there, that's going to be pi over 3 and negative pi over 3, but it asks for on the interval 0 to 2 pi, so we'll call that 5 pi over 3. And those are going to be my solutions. Or I guess the x-coordinates of my intersection. So I'll move over to number 2. Again, I'll set these two things equal to each other. 2 cosine squared x plus 1 equals negative 3 cosine x. All right, and I'm going to set this thing equal to 0, and I think we're going to have to try pretty hard on the factoring here. Plus 3 cosine x plus 1 equals 0. Yeah, okay, so I'm going to go off to the side and do some factoring. I'll just, I'm doing green. So I'll say, all right, if I had 2t squared plus 3t plus 1, I'd be looking for two numbers that multiplied to 2 times 1, the outside two numbers, and added to 3. That would be 2 and 1. So I'm going to split up that middle term into the 2t and 1t. And, if you can see how this one's going to factor, good for you. Just go ahead and factor it like that. If not, I'm just going to remind you, because it's been a really long time since we factored like this in this class. So 2t multiplied by t plus 1, and then I don't have anything to factor over there, so I need to factor out just a 1 times t plus 1. Kind of running out of room, but that's going to be a 0 there. Let's see, maybe. Nope, I can't move that at all, but maybe I could zoom out a little bit. Nope, either way, that's just not going to be able to be something you're going to be seeing. All right, and then I can factor it with 2t plus 1 times t plus 1. We've done this before. All right, so going back over to the original equation, that's going to be factoring with 2. This is basically t equals cosine x, so 2 cosine x plus 1 multiplied by cosine x plus 1. That's going to equal 0. And so one of these factors has to equal 0. Either 2 cosine of x plus 1 equals 0, or maybe cosine of x plus 1 equals 0. And then we just start solving these equations separately. Let's see, that'll be -1, and then we're going to go to a circle. All right, when cosine x equals -half, that's not very far over. That's going to be equivalent to the short leg of a 30, 60, 90 triangle. So, going up, have that one and this one. That's going to be 2 pi over 3 and 4 pi over 3. And then where cosine x equals -1, well, that can only happen at the far left edge of the circle, and that's where x is equal to pi. And so those are going to be all of the coordinates of the intersections. All right, now this one is going to be, all right, so 2 sine x cosine x equals negative cosine x. We're going to start by setting them equal to each other. I'm going to add to both sides to get it set to 0. Think to myself, what do both of these things I'm adding together have in common? A cosine x, and then I'm left with a 2 sine x plus 1. So either cosine x equals 0, or maybe 2 sine x plus 1 equals 0. And, all right, cosine x equals 0, that's already solved down to where it's ready for the circle. I need to solve for sine x. I'll subtract 1 and divide by 2, and then I'll be ready to go. Okay, for cosine x equaling 0, I think we did one very similar to this at the beginning. That's going to be x equals pi over 2 and x equals 3 pi over 2. And where sine x equals -half, that's not very far down. Okay, so that would be like again, that's the short leg of a 30, 60, 90 triangle, and that's going to correspond to a 30-degree reference angle. And so that'll be here and there, and that'll be 7 pi over 6 and negative pi over 6, which is 11 pi over 6. And those are going to be my solutions between 0 and 2 pi. Okay, for this next one, I'm just going to start kind of waiting for when am I going to need to use an identity here. But these might just be all the factoring ones that we were originally going to put on the first day, but then we decided to save for today, which I think was a good idea. Because those Pythagorean identities, they really aren't too bad. So I'm going to factor out 1 power of sine x, and I'll be left with 2 sine x minus 1. See, we really like these ones where it equals a half, it looks like. So either sine x equals 0 or 2 sine x minus 1 equals 0. And that would happen, give myself a little more room, yeah, I can do that. And that would be where sine x equals add 1 divided by 2. And I'll be ready to, that was, okay, it knew what I wanted. There we go. All right, first, sine x equaling 0. Okay, no displacement from the x-axis. That would be here and there. So that would be, let's start making my list of solutions over here. X equals 0, x equals pi, and I think it was a closed interval. Not that it really matters, though. Those like super boundary cases, if you include the last one or don't. I guess maybe it does. We'll have to look at free response question number 4 on the AP exam. We'll see where it really, does it matter or does it not? Sine x equaling 1/2. Okay, so sine is the vertical displacement. Maybe this time I'll actually show it. The vertical displacement's a half. A half is the short leg of a 30, 60, 90 triangle, so the long leg is going to be the horizontal leg. And then I'll draw the hypotenuse, and that's a 30-degree reference angle, so I know I'm sitting like there and there. And that's why I always say, all right, 1/2, not very far up. Okay, so that's pi over 6 and 5 pi over 6. Okay, now we've got 3 secant squared x plus 6 equaling negative 9 secant x. All right, 3 secant squared x plus 6 equaling negative 9 secant squared. Nope, 1 power of secant. All right, so that would be 3 secant squared x plus 9 secant x plus 6 equaling 0. I'm going to divide this whole equation by 3. Plus 3 secant x plus 2 equaling 0. Okay, this one I could not immediately see how it factored, and if that ever happens to you, just like take it out of the trig world and just say, okay, well, I've got 2 powers of secant, then 3 times 1 power of secant and plus 2. That's t squared plus 3t plus 2. And then that's going to be a little easier for me to factor, to look at. All right, and so now I can go back and I can start working with this. This is going to be secant x plus 2 times secant x plus 1 equaling 0. So that's secant x equaling negative 2 and secant x equaling negative 1. Pardon me, I usually like to write out the step where I say, all right, secant x plus 2 equals 0 or secant x plus 1 equals 0. But, you know, this is AP Precal, so I think y'all have got it on these steps. What I definitely need to write out is, all right, if secant x is negative 2, cosine x is 1 over negative 2, that's negative half. And if secant x equals negative 1, cosine x equals 1 over negative 1, which is going to equal negative 1. And then I will go make myself a circle. And say, all right, cosine x equals negative half. All right, so that would be not very far to the left. So that's going to be here and there from the y-axis. All right, so that's 2 pi over 3 and 4 pi over 3. Then I'll think about where is cosine x equaling negative 1, and that would be at the far edge of the circle, and that would be where x equals pi. And those would be the x-coordinates of intersection for those two functions. The last one, nope, this isn't, yeah, this is just going to be one more with just kind of like standard factoring. So set them equal to each other, 2 sine squared x plus 1 equals sine x plus 2. All right, set it to 0. Okay, I'm going to need some help factoring this. So I'm going to multiply the 2 and negative 1 and think about two numbers that multiply to negative 2 while adding to negative 1. So that would be negative 2 and positive 1. So 2t squared minus 2t plus t minus 1 equals 0. And then 2t times t minus 1, yep, plus 1 times t minus 1 equaling 0. And then I'll factor out the t minus 1 and be left with 2t plus 1. There we go. And then, all right, so sine of x is t, subtract 1, multiplied by 2 sine x plus 1, that's going to equal 0. All right, then I'm going to set each of these things equal to 0, so sine x minus 1 could equal 0, or maybe 2 sine x plus 1 could equal 0. This one would be where sine x equaled negative 1/2, and this is definitely something we've solved already, but maybe not this sine x equals 1. So I'll get a circle. Start with, all right, sine x equaling 1. Vertical displacement from the x-axis, positive 1. That's only pi over 2. And then sine x equals negative 1/2. Vertical displacement from the x-axis, negative 1/2. That's really not very far, just 30 degrees worth. And, well, that's supposed to look like 7 pi over 6 and 11 pi over 6. All right, so then that's definitely good equation solving. That's just the type of practice you need, but that was, kind of a lot. Yeah, because we are not even done yet, and we haven't even gotten on the Pythagorean identities one, but I think this is one where we'll need it. So if we start to set sine squared x plus cosine x equal to 1, yeah, this isn't going to work for us. This is going to be bad news. So I need to apply a trig identity. Alright, so we just learned sine squared x plus cosine squared x equals 1, and we might need to use this to substitute to solve an equation. So I'm going to solve for that sine squared x because I can't factor with a cosine, but maybe if I had cosine squared, I could get this worked around to something I could factor. So the thought is we're going to solve for sine squared x by subtracting a cosine squared x from both sides of that equation. And so all of the Pythagorean identities are going to start from that equation highlighted in yellow. All right, so I'm going to go in there and I'm going to say 1 minus cosine squared x. That's what I'm substituting. And so I'll have that here plus a cosine x. That's going to equal 1. Okay, well, adding the parentheses aren't really doing anything. I'm going to subtract 1 from both sides, and I'm going to get negative cosine squared x plus a cosine x equals 0. And maybe I'll factor out a negative cosine x. Or you could factor out a positive, and you'll end up with the same thing. I'd be left with 1 power of cosine x and a minus 1. And then one of these things is equal to 0, either negative cosine x equals 0 or cosine x minus 1 is equal to 0. Negative cosine x equals 0 only when cosine x equals 0, and this would happen when cosine x equaled 1. Alright, so cosine x equaling 0, I'll do that one first. That's going to be the horizontal displacement from the y-axis is 0. That's at the top, and the bottom, that's x equals pi over 2 and 3 pi over 2. And then when cosine x equals 1, when the horizontal displacement from the y-axis is positive 1, that's over there at the far right edge of the circle, that would be x equals 0 and x equals 2 pi. Okay. Alright, I think this one's going to work very similarly. What's the difference? There is no difference. Sine squared plus cosine, and then, equaling negative 1. Well, okay. Let's take a step back for a second then. What's going to change? Not a whole lot. It's just instead of having 0 right there, I'm going to end up with 2. So, all right. Yeah. But maybe it'll be good practice for us to start over. Sine squared x plus cosine x equals negative 1. All right, it's the same substitution, so I'm going to say 1 minus cosine squared x plus cosine x equaling negative 1. I'm going to add 1 to both sides, so I'm going to have 2 minus cosine squared x plus cosine x equaling 0. And then I'm going to rearrange these terms and probably factor out a negative 1. Yeah, minus cosine x minus 2 equals 0. Yeah, I'll like that a lot better for factoring because I can factor that with cosine x minus 2 times cosine x minus 1. Right, if it was t squared minus t minus 2, that's t minus 2 times t plus 1. Yeah, that would not. Yeah, I need a plus there. And that'll equal 0. Alright, so the negative could never equal 0. The cosine x minus 2 could equal 0 if cosine x could equal 2. But that's not going to happen, so that's not contributing any solution. But that doesn't mean that the whole equation is impossible to solve. right? If this other thing on the right equaled 0, if this cosine x plus 1 equaled 0, that would be where cosine x equaled -1, then I could have a solution to the equation. And that is going to be possible. Cosine x can equal -1. So a circle, I think about where that horizontal displacement from the y-axis is -1. That's at the far left edge of the circle. And that's x equals pi only. Okay, here we go. And I knew these were going to come in eventually. All right, tangent squared x plus secant x equals 3. All right, so what we saw in the lesson was that, sine squared plus cosine squared equals 1. That's the one we have to just know. But then tangent and secant are related, and so are cosecant and cotangent, but in ways that we don't necessarily need to memorize. What we need to do is just kind of like, well, I guess we need to start by setting these two things equal to each other. Tangent squared x plus secant x equals 3. But then I'm going to write down the formula that we definitely know. And that's sine squared x plus cosine squared x equals 1. And so if I need to get a tangent squared x in here, or really something that involves secant, what I'm going to need to do is divide both sides of this equation by cosine squared x, right? Because the sine squared x over cosine squared x, that'll give me a tangent squared, and the 1 over cosine squared x, that'll be related to secant. All right, so I'm going to divide all of these terms by cosine squared x. Sine squared x over cosine squared x, that's tangent squared x. Cosine squared x over cosine squared x, that's 1. 1 over cosine squared x, that's secant squared x. And so if I can get rid of that tangent squared x, then I'll have something that's hopefully factorable. So I'm going to have tangent squared x, that's what I'm going to solve for, equal to secant squared x minus 1. So I'm going to make that substitution, secant squared x minus 1. And I'm sure I told you in the lesson, I don't have these memorized, right? I don't feel like I need to. Can't ever remember if it's 1 minus or minus 1, who cares, right? And we can just figure it out from sine squared x plus cosine squared x equals 1. That's what we have to know. All right, now if I go and try to set this thing equal to 0, wait a minute. Secant squared x minus 1 equaling 3. That doesn't seem factorable. Yeah, it definitely was not going to be. I kind of worked it out the rest of the way, and it was just going to get worse and worse. So we're just going to change that to g of x equals 1, and then we're going to have secant, because I think this is what we were going for, secant squared x plus secant x minus 2 equals 0. I can factor that. That's going to be secant x, two numbers that multiply to -2 while adding to +1. That would be 2 and -1. Right, so that would be where secant x equaled -2. And now that is possible. That happens to be when cosine is -1/2. And we'll be able to find that. Or where secant x equals 1, which is where 1 over cosine x is 1, or cosine x equals 1 over 1. And then I think it will be good to find our solutions. Alright, so where cosine x equals -1/2, right, not very far to the left, that would be about here and there. Those are going to be 60-degree reference angles. Those are pi's over 3, 2 pi over 3, and 4 pi over 3. Then cosine x equals 1. Okay, that's going to be all the way to the right, 1 unit to the right of the y-axis, and that's going to be theta equals 0, so I've got x equaling 0 there. And I guess 2 pi. All right, number 10. This one's got cotangent and cosecant in it, so I'm going to kind of do something similar. I'm going to say, all right, first I'm going to set them equal to each other. Cotangent squared x plus 3 equals 3 cosecant x. I'm going to set it to 0. Minus 3 cosecant x plus 3 equals 0. And now I'm going to need to do some trig identity work. We start with the one we have to know. And in this one, if I need a cotangent, I'm going to need to divide both sides by sine squared. So I'd have 1, when I get sine squared over sine squared, cosine squared over sine squared is cotangent squared, and 1 over sine squared is cosecant squared. All right, I need to get rid of that cotangent squared, so I'm going to solve for it over in green. Cosecant squared x, subtract 1. All right, so cosecant squared x minus 1 minus 3 cosecant x plus 3, that's going to equal 0. So minus 1 plus 3, that's positive 2 cosecant squared x minus 3 times 1 power of cosecant, and then add 2, that equals 0. Okay, this should be factorable. Yeah, minus 2 minus 1. So cosecant x minus 2 multiplied by cosecant x minus 1 is going to equal 0. That happens when cosecant x is equal to 2 or when cosecant is equal to 1. I'm going to need to get this in terms of sine so I can actually figure out what's going on the unit circle. Sine is 1/2 or sine is 1 over 1. So it's just going to be 1. The unit circle. Okay, so I don't think that was very straight. It's not a whole lot better. All right, let's just give it one more chance. That's just going to have to do. Do the best we can. Right now, evidently, that's the best I've got. So, sine x equals 1/2. That's a little bit above the x-axis, 30 degrees up. So that's going to be pi over 6 and also 5 pi over 6. And then sine x equals 1. That's all the way up above the x-axis. At the very top of the unit circle, that's x equaling pi divided by 2. Okay, now this one, I just haven't seen one like this. I didn't know this was, but I think I see what's going to happen. All right, I think we're going to wait to, apply a trig identity until we're certain we need to. Yeah. I'm not sure where this one's headed. So what I'm saying is I'm going to do some FOIL, right? I'm going to multiply the first 2, and I'm going to get a sine squared x. The outside 2 would be cosine squared x. Okay, I'm just going to block those off for now. Hopefully you see why. Outside, the inside is cosine x sine x, and maybe I broke the FOIL rule, but it's all gonna be the same. I'm gonna end up with 2 times cosine x times sine x, which is the same as sine x cosine x. Alright, so that thing in yellow highlighter, that's sine squared x plus cosine squared x, that's got to be 1 for any x. So 1 plus this thing, and I'm just going to say 1, maybe I'll copy it in. But what I'm going to do is I'm going to subtract these 2 sine x cosine x's from both sides, and I'm going to get that 1 equals 0. And that's going to be bad news, right? That's going to be telling me that this equation has no solution. I mean, I didn't divide both sides by anything yet. That's not going to have any solution at all. So I guess I could say that the graphs of f and g don't intersect. Okay, now this last one's got a tangent squared x in it, so I can tell I'm already going to need that trig identity. I already did that work once, so I'm just going to bring it over with us and say, all right, tangent squared x. Maybe I'll just substitute it on it right now. But wait a second, why would that... I think I may have tricked myself. Tangent squared x plus sine x equals sine x plus 3 squared x. Well, let me work this for a second. The sine x's are going to cancel. I see now. So I'm going to just make the substitution right now. Then secant squared x minus 1 plus sine x equals sine x plus 3. And I'm realizing I guess you wouldn't have even really needed to do that. You could have just had tangent squared x equals 3, and you'd end up with tangent equals plus or minus the square root of 3, which is something we can definitely solve. But I've come this far. I've used the Pythagorean identity, which I think is what you would probably expect to do, it being on this homework. So I'm just going to go and say, all right, subtract sine x from both sides, get secant squared x minus 1 equals 3, add the 1 to both sides, maybe take the square root of both sides, and then rewrite in terms of cosine plus or minus 1 over 2, and then over here, say, all right, well, where does cosine equal positive half? Well, that would be not very far over. Okay, so it would be over here, corresponding to these 30, 60, 90 triangles like that. Those are my pi over 3s. Those are my 60-degree reference angles. So that's x equaling pi over 3 and also 5 pi over 3. But then, cosine could be negative half, which is not very far over this way, which would give me the rest of the pi over 3s. So that would be also x equaling 2 pi over 3 and 4 pi over 3. All right, that was kind of a lot. But now we're going to simplify the following expressions to either a number or a positive or a negative single trigonometric function. So we're just going to kind of do the algebra to them and see what shakes out. And hopefully we can simplify it down to something really simple is what it's saying. So I think with this one, we should be able to just kind of distribute, and then maybe after distributing, I'll write everything in terms of sine and cosine. So 1 times secant squared x. Okay. On the outside 2, that's 1 times negative 1. The inside 2, that's negative cosecant squared x times secant squared x, and that's what we're going to have to work on later. And then the last 2 is positive cosecant squared x. Okay, and then I guess I should probably... I think maybe I'll start with this. I don't know what else to do. All right, so that's 1 over sine squared x multiplied by cosine squared x. That's the yellow thing. I'm just going to stick with that. And that's going to be a cotangent squared x. All right, now I've also got the secant squared x minus 1. So I should probably go off to the side and maybe see if I can get this one, or the cosecant squared and the cotangent squared. I should probably be able to do something with this, right? So I know that sine squared theta plus cosine squared theta equals 1. And I'm going to divide this out to get the cosecant cotangent relationship. So I'm going to divide everything by sine squared theta. All right. So cotangent squared theta equals positive cosecant squared theta minus 1. That's not really helping me. What is going on here? Okay, yeah, I think I'm just going to completely scrap this and just admit I did not see, at the beginning of these 1 minus cosecant and cosecant squared and secant squared minus 1, we should be able to do something with this. Maybe I'll go up above and divide both sides of this equation by cosine squared theta. Okay, so if I want secant squared x minus 1, that's going to be tangent squared x. And then 1 minus cosecant squared x, that's going to be negative cotangent squared. So, yeah, 1 minus cosecant squared theta equals negative cotangent squared theta. Yep. Okay, if we were to multiply this out in terms of sine and cosine, or thinking about cotangent is 1 over tangent, either way, this is going to multiply to equal negative 1. Okay, yeah, and that's, I guess, probably modeling the right thing for you to do if you get frustrated and not sure what's going on. Probably should go back to where you started and just kind of rethink everything. So, all right, tangent squared x minus 1 multiplied by cosine x. All right, I'm going to rewrite this tangent. Well, actually, in light of how the last one went, I should probably go to the Pythagorean identities. So sine squared x plus cosine squared x equals 1. I've got a tangent squared, so I'm going to divide both sides by cosine squared. Tangent squared x plus 1 equals secant squared x. Right, well, I could just multiply both sides of this equation by negative 1. Negative tangent squared x minus 1. That'll just be negative secant squared x. And so, yeah, all right, negative secant squared x, that's negative 1 over cosine squared x, which maybe I'll just write like that. And then I'm multiplying that by cosine x, which I could write like this. I could cancel off one of those powers and get negative 1 over cosine is negative secant x. And so that's a single trigonometric function, positive or negative. All right. Here, negative 1 plus cosine squared x, that's something I can work with. We know that sine squared x plus cosine squared x equals 1. So that's basically cosine squared x minus 1. So I'll subtract 1 from both sides and then subtract the sine squared away, I guess, to figure out what it equals. Equal negative sine squared x. Oh, yeah. So this will equal negative sine squared x times 1 over sine squared x, and that'll equal negative 1. Okay. Well, first things first, sine squared x plus cosine squared x. We know that equals 1. So that's where I'm going to start. Okay, tangent squared x plus 1. I'm sure I should be remembering this by now, but I'm not. So I'm going to go off to the side. Okay, and maybe you can just write this down once on a post-it note or something and just visualize what's going on. But I got to be showing you what's going on in my head, on screen. So tangent squared x, I'm going to divide everything by cosine squared x. So tangent squared x plus 1, that's going to equal secant squared x. All right, so, and then I'm going to multiply that by cosine x. So secant squared x is 2 cosines in the denominator. Then multiplying by 1 power of cosine in the numerator. That's going to be 1 over cosine, which is secant x. Okay, number 17. Sine squared x minus 1, all divided by cosine x. All right. Sine squared x plus cosine squared x equals 1. If I subtract sine squared x minus 1, that would equal negative cosine squared x. So then I would have over here negative cosine squared x divided by 1 power of cosine x is going to leave me 1 power of cosine x in the numerator, and it's still going to be negative. For number 18, 1 plus cotangent squared. I think that's going to be cosecant squared, but it's going to hopefully work out the same as the other one, but best we be certain. Okay, divide both sides of this relationship by sine squared x. 1 over sine squared x is going to be cosecant squared x. Yes. So I've got cosecant squared x divided by negative cosecant x. That's 2 powers divided by 1 power, leaves me 1 power in the numerator. And it's still negative. Okay. All right. Okay, once I accepted the fact that these really came from the Pythagorean identities, I think it really went a lot better. Okay, now this is probably not going to have as much to do with the Pythagorean identities because I'm not seeing any squares. So this oh yeah, I remember this, that we need to add this in. This is going to be where we write everything in terms of sine and cosine and maybe use like a common denominator or something. So let me look back at the, to a product of 2 trigonometric functions, each raised to a power of 1. Okay, that's interesting. We'll figure this out. All right, cosecant is 1 over sine x minus sine x. Well, I want to have a common denominator. So I should probably have a common denominator of sine x. Okay, if I wanted to write the second thing, I guess I'd need to have 1 more power in the numerator than in the denominator. So I'd have sine squared x over sine x. Now I'm starting to, see where this is heading. 1 minus sine squared x divided by sine x. All right, 1 minus sine squared x. That requires an identity. We know that sine squared x plus cosine squared x equals 1 for every x. So 1 minus sine squared x is equal to cosine squared x. Right, so I'm going to have a cosine squared x divided by cosine squared x divided by sine x. So if I want to write this as a product of 2 trigonometric functions, okay, I'm just going to block off these first 2, each raised to the power 1. Well, cosine over sine is cotangent x, and then I've got a cosine x attached to it. And that's what they were looking for. Okay, cotangent plus tangent. Okay, well, I think we should probably be able to do the same thing on this one, and it'll work out. So cotangent is cosine over sine. And then tangent x is sine over cosine. Well, maybe this is going to work out a little different. Now I see what's going to happen. All right, so we want to get a common denominator. We're going to need a common denominator of sine x times cosine x. Cosine x. And on the first one, to get that, I'm going to have to multiply top and bottom by cosine x. So that will give me 2 powers of cosine x in the numerator. Then over here, in order to get sine x cosine x, I'm going to have an extra power of sine x. And when I put these together, I'm going to have a cosine squared x plus sine squared x, which we know is equal to 1. So that's going to equal 1 over sine x cosine x. And then maybe that 1, we could write that as 1 times 1. So you can see what I'm going to do here. I'm going to write this as 1 over sine multiplied by 1 over cosine. So that's going to equal 1 over sine is cosecant x multiplied by 1 over cosine is secant x. Okay, now the last 2 is simplify the following expressions to be single trigonometric functions raised to a power. All right, so I think these will actually be a little easier. All right, 1 minus cosine squared. That looks Pythagorean. We're going to say, all right, probably for one of the last times today, sine squared x plus cosine squared x equals 1. And so 1 minus cosine squared x, that's going to equal sine squared x. Okay, and so I'm going to now have this equaling 1 over sine squared x, which is going to be cosecant squared x. And that was a single trigonometric function raised to a power. Yeah, great. And then this last one, 1 minus cosine squared x. Do we just have that? Yep, and it was sine squared x, so I don't think I need to go through that again. Divided by sine, whoops, called it x. Right? Sine squared theta divided by sine theta cosine theta. Alright, and maybe I'll write this sine squared theta as sine theta times sine theta. And so if I was to cancel off these sine thetas, I'd be left with a sine theta over cosine theta, which is going to be tangent theta to the first power. Okay, they got me. I thought it was going to be raised to a power higher than 1. And that's going to be all of the problems on this homework, so that's all for this video. Thanks for watching.